The system, commonly known as the Bullet Cluster, is catalogued as 1E0657-56, a massive merging galaxy cluster located at a redshift of approximately 0.296. At this redshift, the observed light left the system when the universe was roughly 2/3 of its current age, corresponding to a look-back time of about 3.5 to 4 billion years under standard lambda CDM cosmology. This places the event well after the era of initial cluster assembly, but still within a phase where large-scale structure growth is actively ongoing. The redshift is high enough that the system is not dynamically relaxed, yet low enough that spatial resolution from modern X-ray and optical instruments remains sufficient to resolve internal structure on scales of tens of kiloparsecs. This balance is crucial. Systems at much higher redshift are harder to dissect observationally, while nearby clusters have typically had enough time since major mergers for mass components to partially remix. The total mass of the Bullet Cluster system is on the order of 10 to the power of 15 solar masses, placing it firmly among the most massive gravitationally bound structures in the universe. This mass estimate arises from multiple independent probes, including X-ray temperature measurements of the intracluster medium, galaxy velocity dispersions, and most importantly, gravitational lensing. The lensing-derived mass is particularly informative because it does not rely on assumptions of hydrostatic equilibrium, an assumption that is severely violated during a major merger. Within this total mass budget, only a small fraction is locked into stars within galaxies. The dominant baryonic component is instead the hot intracluster gas, a tenuous plasma heated to temperatures of tens of millions of Kelvin. Even this gas, however, accounts for only a minority of the total mass inferred from gravitational effects, a fact that becomes central to the interpretation of the system. The Bullet Cluster is not a single object, but a collision between two galaxy clusters of unequal mass. The smaller subcluster, often referred to as the bullet, has passed through the core of the more massive main cluster. The encounter velocity inferred from X-ray shock diagnostics and dynamical modelling is extraordinarily high, typically estimated at around 4,000 to 4,500 kilometers per second. Such velocities are not measured directly, but reconstructed from the properties of the bow shock observed in X-ray images, the temperature jump across that shock, and the relative position of the mass components. The inferred Mach number of the shock, roughly 3, implies supersonic motion through the intracluster medium, whose sound speed is set by its extreme temperature. These velocity estimates carry uncertainties related to projection effects, assumptions about the pre-shock gas state, and the exact merger geometry. But even conservative analyses place the collision velocity at the upper end of what is expected in standard cosmological simulations. The geometry of the merger plays a decisive role in how cleanly the system can be interpreted. Observations indicate that the collision occurred primarily in the plane of the sky rather than along the line of sight. This conclusion is drawn from the sharpness of the observed shock front, the distinct spatial separation between mass components, and the relatively modest line-of-sight velocity difference measured between the galaxy populations of the two clusters. If the merger were oriented mostly along the line of sight, projection would smear out spatial offsets and complicate lensing reconstructions. Instead, the near plane of sky orientation allows the different physical components, galaxies, gas, and total mass, to be mapped with minimal ambiguity. This geometry effectively turns the Bullet Cluster into a natural experiment in collision dynamics, where spatial separation corresponds closely to physical separation rather than being dominated by projection effects. A defining feature of the Bullet Cluster is that it is observed shortly after core passage, the moment when the dense cores of the two clusters crossed one another. Numerical simulations of cluster mergers show that this phase is brief on cosmological timescales, lasting only a few 100 million years before gravitational forces begin to recenter the components and erase clear separations. Observing the system at this specific stage means that the effects of the collision are still dynamically fresh. The intra-cluster gas of the smaller cluster has been stripped and shocked, lagging behind the galaxies and the dominant mass component. The galaxies themselves, being sparsely distributed and effectively collisionless on these scales, have passed through largely unaffected. The gravitational potential wells associated with each cluster remain closely aligned with the galaxy distributions rather than with the displaced gas. This timing is not incidental. If the system were observed significantly earlier, before core passage, the components would still be largely coincident, offering little insight into their differing physical behaviors. If observed much later, gravitational attraction and dynamical friction would begin to pull the gas back toward the potential minima, partially realigning baryons and total mass. The bullet cluster sits in a narrow temporal window where separation is maximal and observationally resolvable. This makes it uniquely valuable as an astrophysical laboratory for disentangling the roles of gravity, baryonic physics, and any non-luminous mass component. High-velocity dissociative mergers like the bullet cluster are rare. Large cosmological simulations predict that collisions between massive clusters do occur, but encounters with such extreme relative velocities and favourable geometries are uncommon. The rarity arises from the statistical distribution of cluster masses, relative velocities set by large-scale gravitational potentials, and the requirement that the system be observed at just the right stage of the merger. While rarity does not diminish the physical significance of the event, it does mean that each such system carries substantial weight in shaping interpretation. The bullet cluster was the first system in which all these conditions aligned: sufficient mass, high collision speed, plane of sky orientation, and high-quality multi-wavelength data. The dissociative nature of the merger is central to its scientific importance. In a dissociative merger, different components of the system respond differently to the collision. The hot gas experiences ram pressure and shock heating, causing it to slow down and separate spatially. The galaxies, composed mostly of empty space on these scales, pass through with minimal direct interaction. The dominant mass component inferred from gravitational lensing follows the galaxies rather than the gas. This behavior directly reflects the underlying physical properties of each component. Gas interacts electromagnetically and thermodynamically. Galaxies interact primarily through gravity. The dominant mass component interacts gravitationally, but shows little evidence of significant non-gravitational interaction during the collision. Timing matters because it allows these interaction properties to manifest spatially. The bullet cluster effectively freezes a transient moment when the outcomes of different interaction regimes are visible simultaneously. The gas has been slowed and heated but not yet fallen back. The galaxies have moved ahead but remain within the overall gravitational potential. The total mass distribution traced by lensing reveals where most of the gravitating matter resides at this moment. This simultaneous visibility is what allows strong, relatively model-independent conclusions to be drawn. The system's redshift further enhances its interpretive power. At Z approximately 0.296, background galaxies suitable for weak gravitational lensing measurements are abundant, enabling high-quality shear maps. The lensing signal is strong due to the cluster's mass, reducing statistical noise and allowing mass centroids to be localized with relatively small uncertainties. Combined with X-ray observations that trace the hot gas with high spatial resolution, the bullet cluster offers a rare convergence of observational clarity across different physical probes. In sum, the bullet cluster is not important merely because it is massive or visually striking. Its significance lies in the conjunction of scale, speed, geometry, and timing. It is a system caught in a fleeting phase where gravitational dynamics and baryonic physics pull apart the components of a galaxy cluster in a way that can be directly observed. This separation sets the stage for the deeper inference that follows: the identification of a dominant mass component that behaves neither like gas nor like stars, but instead follows the collisionless dynamics expected of dark matter. A galaxy cluster is not a simple aggregation of galaxies bound together by gravity. It is a multi-component physical system in which different forms of matter contribute very unevenly to the total mass, occupy different volumes, and obey different physical laws. Understanding these components, how much mass each contains, how they are distributed in space, and how they interact, is essential for interpreting systems like the bullet cluster and for avoiding common misconceptions that arise from relying on visible matter alone. When the mass budget of a massive galaxy cluster is decomposed, three components dominate: hot intracluster gas, stars bound in galaxies and in diffuse intracluster light, and a dominant non-luminous component inferred from gravity, commonly identified as dark matter. In rich clusters with total masses around 10 to the power of 15 solar masses, the hot gas typically accounts for about 10 to 15% of the total mass. Stars contribute only a few percent, often less than 3%. The remaining 80 to 85% of the mass is not directly visible at any wavelength and is inferred through its gravitational influence. This breakdown is not arbitrary or model dependent. It is supported by multiple independent measurements across many clusters and over a wide range of redshifts. The intracluster medium is the most massive baryonic component of a galaxy cluster. It consists of a fully ionized plasma, primarily hydrogen and helium, with trace amounts of heavier elements heated to temperatures ranging from roughly 30 million to over 100 million Kelvin. At these temperatures, atoms are completely stripped of electrons, and the gas emits strongly in the X-ray portion of the electromagnetic spectrum through thermal bremsstrahlung and line emission from highly ionized heavy elements. Typical particle densities in the intracluster medium are extremely low by terrestrial standards, often between 10 to the power of -4 and 10 to the power of -2 particles per cubic centimetre. Yet the enormous volume of the cluster makes the total gas mass substantial. The X-ray brightness of this gas depends sensitively on density. For thermal bremsstrahlung, the emissivity scales approximately with the square of the electron density. This means that relatively small increases in gas density lead to disproportionately large increases in X-ray brightness. As a result, X-ray images of clusters are heavily weighted toward the densest regions of the gas, typically near the cluster core or along shock fronts in merging systems. This density-squared dependence is crucial for interpreting X-ray observations correctly. Bright X-ray emission does not necessarily indicate where most of the mass is. It indicates where the gas is densest. In dynamically active systems, this distinction becomes especially important. The spatial distribution of the intracluster gas differs markedly from that of the galaxies. Gas responds strongly to pressure forces, shocks, and viscosity. In relaxed clusters, it tends to settle into a roughly spherical distribution centered on the cluster's gravitational potential minimum. In merging clusters, however, the gas can be displaced, compressed, or stripped entirely from its original location. Shock fronts, contact discontinuities, and temperature gradients are common. These features encode information about the merger history and gas dynamics, but do not directly trace the total gravitational mass. Galaxies, by contrast, are effectively collisionless on cluster scales. The typical separation between galaxies is large compared to their physical sizes, and direct collisions between stars or galaxies during a cluster merger are exceedingly rare. As a result, galaxies move primarily under the influence of gravity, following trajectories determined by the cluster's gravitational potential. Their spatial distribution therefore provides a better tracer of the underlying gravitational field than the gas does, particularly during mergers. However, galaxies represent only a small fraction of the total mass, and their light output can be a misleading guide to where most of the mass resides. The stellar component of a cluster includes stars bound within galaxies, as well as a diffuse intracluster stellar population. This intracluster light arises from stars that have been stripped from galaxies during interactions and mergers over the cluster's history. While intracluster light can contribute a non-negligible fraction of the total stellar luminosity, its total mass contribution remains small compared to both the gas and the dominant dark component. Stellar mass-to-light ratios, constrained by stellar population synthesis models and observations of galaxy dynamics, limit how much mass can be hidden in stars without violating other well-established constraints. Typical baryon fractions in massive clusters closely match the cosmic baryon fraction inferred from measurements of the cosmic microwave background. This agreement is significant. It indicates that clusters, as the largest gravitationally bound systems in the universe, retain most of their baryons and therefore provide a fair sample of the universe's matter content. Within clusters, however, baryons are distributed unevenly between gas and stars, with gas overwhelmingly dominant. The fact that the total baryonic mass still falls far short of the mass inferred from gravitational measurements implies the presence of a substantial non-baryonic component. Galaxies trace gravitational potential wells because their motions are governed almost entirely by gravity. The velocity dispersion of galaxies within a cluster reflects the depth of the cluster's potential well, and their spatial distribution tends to align with regions of higher gravitational potential. This makes galaxy positions and velocities useful probes of cluster mass in relaxed systems. However, galaxy-based mass estimates rely on assumptions about dynamical equilibrium that break down during major mergers. In such cases, galaxies can still trace the potential wells associated with individual subclusters, but their velocity distributions become more complex and anisotropic. The dominant mass component inferred from gravitational lensing behaves similarly to the galaxies during mergers, not because galaxies dominate the mass, but because both are effectively collisionless. This shared behavior is a key observational fact. The gas lags behind due to ram pressure and shock heating, while the galaxies and the dominant mass component move ahead. This separation highlights the fundamentally different physical interactions governing each component. Visible matter is misleading for mass inference because brightness does not scale linearly with mass. X-ray brightness is biased toward dense gas. Optical brightness is biased toward regions of active star formation or high stellar density. Neither directly reflects the total gravitational mass distribution. In relaxed clusters, these biases can sometimes be corrected through modeling, but in dynamically active systems, they can lead to profoundly incorrect conclusions if taken at face value. Gravitational lensing provides a way around these limitations because it responds directly to mass, regardless of its composition or physical state. Lensing measurements reveal that the majority of a cluster's mass is not co-located with the brightest X-ray emitting gas, nor with the bulk of the stellar light. Instead, it resides in extended halos that dominate the gravitational potential. This conclusion holds across many clusters and is particularly striking in merging systems where the different components are spatially separated. The combination of gas physics, stellar dynamics, and gravitational lensing paints a consistent picture of galaxy clusters as systems dominated by a non-luminous mass component. The intracluster gas reveals the thermodynamic and hydrodynamic state of the cluster. The galaxies trace the gravitational potential wells and record the cluster's assembly history. Gravitational lensing reveals the total mass distribution directly. Only by considering all three together can the structure and evolution of clusters be understood. In systems like the bullet cluster, these distinctions become impossible to ignore. The brightest component in X-rays is not the most massive. The most massive component does not emit light. The galaxies, though visually prominent, contribute only a small fraction of the mass, yet move in step with the dominant gravitational component. This decoupling of mass and light is not an anomaly, but a direct consequence of the physical properties of the components involved. Understanding the components of a galaxy cluster is therefore not a matter of cataloguing what is visible. It is a matter of recognizing that different forms of matter leave different observational signatures and that only gravity provides a universal accounting. Once this framework is established, the significance of systems like the bullet cluster becomes clear. They reveal in a single snapshot how these components behave when subjected to extreme dynamical stress, and why visible matter alone cannot be trusted to tell the full story of mass in the universe. When two galaxy clusters collide, the event is governed by a hierarchy of physical interactions that act very differently on gas, stars, and the dominant gravitating mass. The slowing of gas during such encounters is not a subtle effect, it is a direct and inevitable consequence of plasma physics operating on megaparsec scales. Understanding why the intracluster gas decelerates while galaxies do not requires following momentum exchange, shock formation, and energy dissipation from first principles without assuming equilibrium or steady-state behavior. The intracluster medium is a diffuse, ionized plasma permeating each cluster. Although its density is extremely low by laboratory standards, it is sufficiently dense that collective electromagnetic interactions dominate its behavior. When two clusters approach one another at thousands of kilometers per second, their gas components cannot pass through each other freely. Instead, they interact through long-range Coulomb forces mediated by electric and magnetic fields. This interaction manifests macroscopically as ram pressure, shocks, and heating. Ram pressure stripping arises when a body of gas moves through another gas at high relative velocity. The pressure exerted on the moving gas is proportional to the density of the ambient medium multiplied by the square of the relative velocity. In a cluster collision, the subcluster's gas encounters the dense core gas of the main cluster at supersonic speeds. The resulting ram pressure exceeds the gravitational restoring force that originally bound the gas to its dark matter halo. Once this threshold is crossed, gas is displaced backward relative to the motion of the subcluster, effectively peeling it away from the collisionless components. This stripping is not instantaneous, but occurs over a characteristic timescale set by the momentum exchange rate between the two gas bodies. As ions and electrons from the opposing plasmas interpenetrate, electromagnetic interactions transfer momentum efficiently. Unlike stars or dark matter particles, which interact primarily through gravity and rarely collide, charged particles experience continuous interactions even at low densities. The cumulative effect is a rapid deceleration of the gas relative to the cluster's center of mass motion. Shock heating is a central feature of this process. Because the relative velocity of the collision exceeds the local sound speed of the intracluster medium, information about the oncoming gas cannot propagate upstream fast enough to allow smooth adjustment. Instead, a shock front forms. Across this shock, gas properties change discontinuously. Density increases, temperature rises sharply, and kinetic energy associated with bulk motion is converted into random thermal motion of particles. The Rankine-Hugoniot conditions describe these changes quantitatively, relating pre-shock and post-shock states through conservation of mass, momentum, and energy. It is important to distinguish shock heating from adiabatic compression. Adiabatic compression occurs when gas is compressed slowly enough that no heat is exchanged with the surroundings, and entropy remains constant. In this case, temperature rises smoothly as density increases. Shock heating, by contrast, is inherently non-adiabatic. Entropy increases across the shock, and irreversible processes dominate. In cluster mergers, both effects can occur, but the presence of sharp temperature and density jumps, along with entropy generation, indicates that shock heating is the dominant mechanism during the most violent phases of the collision. The effectiveness of shocks in slowing gas depends on the plasma's collisional properties. In the intracluster medium, the classical Coulomb mean free path for particle-particle collisions can be large, sometimes comparable to or exceeding the characteristic size of observed shock features. At first glance, this might suggest that the gas should behave nearly collisionlessly. However, this conclusion is misleading because collective plasma effects dominate over simple binary collisions. Electromagnetic fields generated by charge separations and currents couple particles together over length scales much larger than the Coulomb mean free path. As a result, the plasma behaves as a fluid on cluster scales, supporting shocks and pressure gradients despite its low density. The formation of a coherent shock front therefore does not require frequent direct particle collisions. Instead, it arises from collective interactions mediated by fields which enforce macroscopic conservation laws. This is why the intracluster medium can sustain sharp shock structures even when the microscopic mean free path appears large. The observed shock in the bullet cluster provides direct evidence that the gas behaves as a collisional fluid in this collective sense. Galaxies behave very differently during the same collision. A typical galaxy occupies a volume many orders of magnitude smaller than the average separation between galaxies in a cluster. Stars within galaxies are even more sparsely distributed relative to their sizes. The probability of direct star-star or galaxy-galaxy collisions during a cluster merger is effectively negligible. As a result, galaxies experience almost no non-gravitational forces during the encounter. They respond only to the large-scale gravitational potential of the system. This is why galaxies can be treated as test particles in cluster collision dynamics. They trace the gravitational potential without significantly altering it, and without being significantly slowed by the surrounding gas. Their trajectories are determined by the pre-existing potential wells of the merging clusters and by the evolving combined potential during the merger. While tidal forces can distort galaxies over longer timescales, these effects are secondary during the brief, violent phase of core passage. The contrast between gas and galaxies highlights the importance of momentum transfer timescales. For gas, the timescale for momentum exchange through electromagnetic interactions is short compared to the duration of the merger. This allows substantial deceleration and energy dissipation to occur over tens to hundreds of millions of years. For galaxies, the momentum exchange timescale through non-gravitational interactions is effectively infinite on merger timescales. Gravity redistributes momentum between galaxies and the cluster potential, but it does not dissipate energy in the same way. As gas slows, its kinetic energy does not vanish, it is transformed. The bulk kinetic energy associated with coherent motion is converted into internal energy of the plasma. Particle velocities become randomized, raising the temperature of the gas. This thermal energy then manifests observationally as enhanced X-ray emission. Because X-ray emissivity depends strongly on both temperature and density, shock-heated regions become bright traces of where energy dissipation has occurred. Energy dissipation into thermal modes has long-term consequences for cluster evolution. The heated gas has higher entropy and resists recollapse into the deepest parts of the gravitational potential. This affects the subsequent cooling history of the cluster and influences star formation rates in cluster galaxies. In merging systems, the spatial distribution of entropy provides a record of past shock activity and energy injection. A further consequence of differing responses between gas and collisionless components is the formation of contact discontinuities. These are surfaces separating regions of gas with different densities and temperatures, but similar pressures. In cluster mergers, a contact discontinuity often forms between gas originating in the subcluster and gas belonging to the main cluster. On one side of the discontinuity, gas may be cooler and denser, on the other, hotter and more rarefied. The sharpness of these boundaries indicates suppressed mixing, often attributed to magnetic fields aligned with the interface, which inhibit transport across the boundary. Contact discontinuities are distinct from shock fronts. While shocks involve irreversible changes and entropy production, contact discontinuities represent boundaries between fluids that have already been processed by shocks or compression. Their presence provides additional information about the merger geometry, velocity, and plasma microphysics. In the bullet cluster, the prominent bullet-shaped cold front is an example of such a discontinuity, marking the leading edge of the subcluster's gas core as it moves through the hotter ambient medium. Taken together, these processes explain why gas slows down during cluster collisions. Ram pressure strips gas from its original gravitational well. Shocks convert kinetic energy into heat and generate entropy. Collective plasma interactions enforce fluid behavior despite low densities. Momentum transfer occurs efficiently for gas, but negligibly for galaxies. Energy is dissipated into thermal modes rather than remaining in bulk motion. Contact discontinuities preserve sharp boundaries between different gas populations. This physics is well understood and does not rely on exotic assumptions. It follows directly from applying known plasma and fluid dynamics to the extreme but well-defined conditions of galaxy cluster mergers. The slowing of gas is therefore not an interpretive choice but a physical inevitability. Once this behavior is established, the contrasting behavior of galaxies and the dominant gravitating mass becomes a powerful diagnostic tool. It allows observers to separate components based on their interaction properties and to infer the presence of a collisionless mass component that behaves like galaxies rather than like gas. In this sense, cluster collisions act as natural experiments in which different forms of matter are subjected to the same gravitational impulse but respond according to their intrinsic physical properties. The gas slows because it must. The galaxies do not because they cannot. The significance of this contrast becomes fully apparent only when the distribution of total mass is examined, revealing that most of the mass follows the collisionless components rather than the luminous plasma. The identification of a clear shock front in the bullet cluster rests fundamentally on X-ray observations, and in particular on data obtained by the Chandra X-ray Observatory. Chandra's importance is not merely historical, its technical characteristics are uniquely suited to resolving the fine spatial and spectral structure required to diagnose shocks in the intracluster medium. With sub-arcsecond angular resolution and low instrumental background, Chandra can resolve sharp surface brightness edges and temperature gradients on scales of tens of kiloparsecs at the redshift of the bullet cluster. This capability is essential because shock fronts in cluster mergers are geometrically thin compared to the overall cluster size, and any significant blurring would smear out the diagnostic features needed to distinguish shocks from other discontinuities. In X-ray images of the bullet cluster, the most striking feature is a sharp, arc-shaped brightness edge located ahead of the dense gas core of the smaller subcluster. This edge is convex in the direction of motion, consistent with a bow shock formed by a supersonic object moving through a fluid. The surface brightness increases abruptly across this edge, indicating a sudden increase in gas density. The sharpness of the edge is itself informative. It implies that diffusion and mixing across the boundary are suppressed on observable timescales, reinforcing the interpretation of a coherent shock structure rather than a gradual transition. Temperature measurements across the shock provide the decisive evidence that the brightness edge is indeed a shock front rather than a contact discontinuity. Chandra's spectroscopic capability allows the X-ray spectrum of the gas to be measured in narrow regions on either side of the edge. These spectra reveal a clear temperature jump, with the post-shock gas significantly hotter than the pre-shock gas. In the bullet cluster, temperatures rise from roughly 7 to 8 keV ahead of the shock to more than 15 keV behind it, corresponding to an increase from around 80 million Kelvin to well over 150 million Kelvin. This abrupt temperature increase is a hallmark of shock heating and cannot be produced by adiabatic compression alone. The combination of density and temperature jumps allows the shock to be quantitatively characterized using the Rankine-Hugoniot conditions. These relations follow directly from conservation of mass, momentum, and energy across a shock front in a fluid. For a given ratio of post-shock to pre-shock density, the Rankine-Hugoniot equations predict a corresponding temperature jump and constrain the Mach number of the flow. In the bullet cluster, the measured density jump across the shock is approximately a factor of 3. When combined with the observed temperature increase, this density contrast is consistent with a strong shock propagating through the intracluster medium. Applying the Rankine-Hugoniot conditions to the observed discontinuities yields an inferred Mach number of roughly 3. This means that the shock is moving at about 3 times the local sound speed of the pre-shock gas. The Mach number is not measured directly, but derived from the observed thermodynamic jumps, and its value depends on assumptions about the equation of state of the plasma and the absence of significant energy losses other than shock heating. The intracluster medium is well approximated as an ideal monatomic gas on these scales, with an adiabatic index close to 5/3, making these assumptions robust. The sound speed in the intracluster plasma sets the reference scale for interpreting the Mach number. In a fully ionized gas at tens of millions of Kelvin, the sound speed is extremely high by everyday standards, typically on the order of 1,000 to 1,500 kilometers per second. This sound speed depends on the gas temperature and composition and reflects how quickly pressure disturbances propagate through the medium. A Mach number of 3 therefore corresponds to a shock velocity of roughly 3,000 to 4,500 km per second, consistent with independent dynamical estimates of the subcluster's motion. The determination of the Mach number relies on several key assumptions that are carefully tested against the data. One assumption is that the shock is viewed close to edge-on, so that projection effects do not significantly dilute the observed jumps. The sharpness of the surface brightness edge and the clear separation between pre-shock and post-shock regions support this assumption. Another assumption is that electron and ion temperatures equilibrate on timescales shorter than the time since shock passage. While equilibration is not instantaneous, the observed temperature structure is consistent with sufficient equilibration, having occurred to make the measured temperatures representative of the bulk plasma. The curvature of the shock front provides additional constraints on the merger geometry. The shock is not planar but curved, with a shape resembling a Mach cone formed by a supersonic object moving through a fluid. The opening angle of this cone depends on the Mach number. Higher Mach numbers produce narrower cones. The observed curvature in the bullet cluster is consistent with the Mach number inferred from the thermodynamic jumps, providing an independent geometric crosscheck. This consistency strengthens confidence in the interpretation and reduces reliance on any single diagnostic. The orientation and curvature of the shock also constrain the three-dimensional motion of the subcluster. A shock propagating primarily in the plane of the sky produces a well-defined arc in projection, whereas a shock oriented significantly along the line of sight would appear more diffuse and less sharply defined. The clarity of the bullet cluster shock indicates that the merger axis lies close to the plane of the sky, an inference supported by galaxy velocity measurements. This geometric alignment is crucial because it minimizes projection uncertainties in both X-ray and gravitational lensing analyses. One of the reasons the bullet cluster shock is so scientifically valuable is its clarity relative to other astrophysical shocks. Shocks are common in astrophysics, appearing in supernova remnants, stellar winds, and jets, but cluster merger shocks operate on vastly larger scales and under very different physical conditions. Many cluster shocks are weak, with Mach numbers barely above unity, making their thermodynamic signatures subtle and difficult to detect. In contrast, the bullet cluster shock is both strong and spatially extended, allowing detailed mapping of its properties. The large physical size of the shock front, spanning hundreds of kiloparsecs, means that it can be resolved into multiple independent regions for analysis. This allows spatial variations in temperature, density, and pressure to be measured and compared with theoretical expectations. The resulting agreement between observation and basic shock physics is remarkably good, lending confidence to the interpretation and reducing the likelihood that the observed features are artifacts of data processing or modelling assumptions. Another factor contributing to the clarity of the bullet cluster shock is the relative simplicity of the pre-shock environment. The gas ahead of the shock is relatively smooth and uniform compared to the turbulent post-shock region. This simplifies the interpretation of the observed jumps and reduces uncertainties associated with complex background structure. In many other clusters, pre-existing substructure and turbulence complicate shock identification, but in the bullet cluster, the contrast is unusually clean. The shock front also plays a critical role in isolating the gas dynamics from the behavior of other components. By providing a direct measurement of the subcluster's velocity relative to the gas, the shock sets the dynamical scale for the entire merger. This velocity can then be compared with the motion of the galaxies and the inferred distribution of total mass. The fact that the galaxies and the dominant mass component are found ahead of the shock, while the gas lags behind, establishes a clear separation between collisional and collisionless behavior. The bullet cluster shock is therefore not just an impressive visual feature, but a quantitative diagnostic tool. It anchors the dynamical interpretation of the system and constrains key parameters such as velocity, orientation, and timing. Few astrophysical systems offer such a direct and internally consistent set of measurements. The combination of sharp density and temperature jumps, well-defined curvature, favourable geometry, and high-quality X-ray data makes this shock one of the clearest and best-studied examples of a high Mach number shock in the universe. This clarity has broader implications. Because the shock properties are so well constrained, uncertainties in the merger dynamics are reduced. This, in turn, strengthens conclusions drawn from comparing gas behavior with the distribution of galaxies and gravitational mass. The shock effectively calibrates the collision, fixing the relative motion and interaction strength of the baryonic component. Once this calibration is in place, deviations between the gas and the total mass distribution cannot be attributed to ambiguities in the merger dynamics. They must instead reflect genuine differences in how various forms of matter respond to the collision. In this way, the X-ray shock front and its associated Mach cone are central to the bullet cluster's role as evidence for dark matter. They establish that the gas behaves exactly as expected for a collisional plasma subjected to a supersonic impact. With that behavior firmly characterized, the contrasting behavior of the dominant mass component stands out in sharp relief, setting the stage for the gravitational lensing analysis that follows. Gravitational lensing provides a direct method for mapping mass in the universe that does not rely on assumptions about dynamical equilibrium, temperature, or the physical state of matter. In systems like the bullet cluster, where violent interactions disrupt the intracluster medium and invalidate hydrostatic methods, lensing becomes the most reliable way to determine how mass is actually distributed. The technique exploits the fact that gravity bends spacetime itself, altering the apparent shapes and positions of background galaxies in a way that depends only on the projected mass along the line of sight. In the regime relevant for galaxy clusters, lensing is typically divided into weak and strong components. Weak gravitational lensing refers to the subtle, coherent distortions imparted to the shapes of large numbers of background galaxies. Individually, these distortions are too small to be distinguished from the galaxy's intrinsic ellipticities, but statistically they produce a measurable shear pattern aligned with the foreground mass distribution. By measuring the shapes of thousands of background galaxies across a wide field, it is possible to reconstruct the shear field induced by the cluster. The reconstruction of the weak lensing shear field begins with careful shape measurement. Observed galaxy images must be corrected for instrumental effects such as point spread function, distortion, pixelization, and noise. Once these corrections are applied, the residual ellipticity patterns are interpreted as a combination of intrinsic galaxy shapes and lensing-induced shear. Averaging over many galaxies suppresses the random intrinsic component, leaving a coherent shear signal that traces the gradient of the gravitational potential. From the measured shear field, one can infer the convergence field, which represents the projected surface mass density normalized by a critical density that depends on the geometry of the lens source system. The convergence is directly related to the mass distribution, though the inversion from shear to convergence is not unique without additional assumptions. This non-uniqueness is known as the mass sheet degeneracy. Adding a uniform sheet of mass changes the convergence but leaves the shear unchanged. In practice, this degeneracy is handled by imposing physically motivated boundary conditions, such as assuming that the mass density approaches zero at large distances from the cluster, or by incorporating independent constraints from strong lensing or dynamics. Strong gravitational lensing occurs in regions where the projected mass density is sufficiently high that light rays from background galaxies are deflected by large angles. This produces highly distorted images such as arcs, arclets, or even multiple images of the same source. In the bullet cluster, strong lensing features are observed near the cores of the merging subclusters. These features provide precise constraints on the local mass distribution because the positions, shapes, and multiplicities of the arcs depend sensitively on the gravitational potential. Strong lensing and weak lensing are complementary. Strong lensing probes the inner regions of the mass distribution with high spatial resolution but over a limited area. Weak lensing probes the mass distribution over a much larger area but with lower resolution. By combining both, it is possible to construct a mass map that is well constrained across a wide range of scales. In the bullet cluster, this combined approach reveals two distinct mass concentrations associated with the galaxy distributions of the two colliding clusters. A crucial ingredient in lensing analysis is the redshift distribution of background galaxies. The strength of the lensing signal depends on the relative distances between the observer, the lens, and the source. Background galaxies at higher redshift experience stronger lensing for a given lens mass. Accurate knowledge of the redshift distribution allows the critical surface density to be computed and the convergence to be translated into an absolute mass scale. In practice, photometric redshifts derived from multiband imaging are used to estimate this distribution. Uncertainties in these redshifts contribute to systematic errors, but are generally well characterized and smaller than the dominant lensing signal in massive clusters, like the bullet cluster. Once the convergence field is reconstructed, it can be visualized as a projected mass map. These maps show where mass is concentrated in the plane of the sky, independent of whether that mass is luminous or dark. In the bullet cluster, the convergence peaks align closely with the galaxy distributions rather than with the X-ray bright gas. This alignment is the central observational result. The majority of the mass follows the collisionless galaxies instead of the collisional plasma. It is important to distinguish between convergence maps and true three-dimensional mass distributions. Lensing measures the integral of mass density along the line of sight, weighted by geometry. As a result, lensing cannot directly distinguish between mass located at different depths along the line of sight. However, in the bullet cluster, the merger geometry is sufficiently simple and the redshift of the system sufficiently well constrained that projection effects are unlikely to produce the observed offsets between gas and mass peaks. Extensive modelling has shown that plausible line-of-sight configurations cannot mimic the observed separation. One of the defining strengths of gravitational lensing is that it is insensitive to the thermodynamic state of matter. Whether mass is in the form of hot plasma, cold gas, stars, or non-baryonic particles, its gravitational influence on space-time is the same. This makes lensing uniquely powerful in systems where gas has been shock-heated, displaced, or otherwise disturbed. X-ray observations may show dramatic changes in brightness and temperature, but lensing remains a faithful tracer of the total mass. This insensitivity also means that lensing does not require assumptions about equilibrium. Traditional mass estimates from X-ray data often assume hydrostatic equilibrium, balancing pressure gradients against gravity. In merging systems, this assumption fails catastrophically. Lensing bypasses this problem entirely. It measures mass directly through geometry rather than dynamics. This is why lensing is the preferred method for mass mapping in disturbed clusters. Despite its strengths, lensing is not infinitely precise. The resolution of a lensing-derived mass map is limited by the density of usable background galaxies and by the intrinsic noise in their shapes. To reduce noise, the shear field must be smoothed over a finite scale, typically tens of kiloparsecs in high-quality data. This smoothing sets a fundamental limit on how sharply mass peaks can be localized. In the bullet cluster, the smoothing scale is small enough that the mass peaks are clearly separated from the gas peak by distances well above the resolution limit. Systematic uncertainties associated with smoothing and reconstruction algorithms have been extensively tested. Different teams using different methods and datasets have reproduced the same qualitative result: two dominant mass peaks aligned with the galaxy distributions. The robustness of this result against methodological variations is a key reason the bullet cluster is regarded as strong evidence rather than a marginal or model-dependent case. Another potential concern is contamination of the background galaxy sample by cluster members or foreground objects. Such contamination would dilute the lensing signal and could bias mass estimates. Careful color and magnitude cuts, along with redshift information, are used to minimize this effect. Residual contamination would tend to weaken the lensing signal rather than create spurious mass peaks, making it unlikely to explain the observed alignment. The combination of weak and strong lensing in the bullet cluster therefore provides a coherent and internally consistent picture of the mass distribution. It shows that most of the mass is concentrated in regions offset from the brightest baryonic component. This conclusion does not depend on the details of gas physics, on equilibrium assumptions, or on uncertain modelling choices. It follows directly from the geometry of space-time as revealed by the distorted images of distant galaxies. Gravitational lensing thus serves as the central mass probe in the bullet cluster. It provides the quantitative foundation upon which interpretations of the system are built. By revealing where the mass actually is, lensing allows the differing behaviours of gas, galaxies, and the dominant gravitating component to be compared on equal footing. This comparison is what transforms the bullet cluster from an interesting merger into a critical test of our understanding of matter in the universe. The defining observational result of the bullet cluster is not the presence of a shock, nor the violence of the collision itself, but the discovery that the dominant mass distribution is spatially offset from the brightest baryonic component. This mass-light offset is the point at which the system ceases to be merely an example of cluster merger physics and becomes a direct test of how matter behaves under extreme conditions. The result emerges from a careful comparison between X-ray maps tracing the intracluster gas and gravitational lensing maps tracing the total projected mass. X-ray observations show that the bulk of the baryonic mass in the system resides in the hot intracluster plasma. Because X-ray emissivity scales roughly with the square of the gas density, the brightest X-ray regions correspond to where the gas is most concentrated. In the bullet cluster, this gas is clearly displaced from the galaxies and trails behind the smaller subcluster, having been slowed by ram pressure and shock heating during the collision. The X-ray peak therefore marks the location of the densest baryonic matter, not the deepest gravitational potential. Gravitational lensing maps, constructed independently of the X-ray data, reveal where the mass responsible for bending light is concentrated. When these maps are overlaid on the X-ray images, a striking offset becomes apparent. The lensing-derived mass peaks do not coincide with the X-ray brightness peak. Instead, they are located ahead of the gas, spatially aligned with the distributions of galaxies in each subcluster. This offset is not subtle or marginal. It is visually and quantitatively clear. The measured separation between the gas peak and the nearest lensing mass peak is on the order of 100 to 200 kiloparsecs. At the redshift of the system, this corresponds to several arcseconds on the sky, well above the resolution limits of both the X-ray and lensing data. The uncertainty in the centroid positions of the mass peaks and gas peaks is much smaller than the observed separation, leaving little room for ambiguity. The offset is therefore not an artifact of limited resolution or centroiding error. The alignment of the lensing peaks with the galaxy centroids is equally important. Galaxies are easily visible in optical images, and their positions can be determined with high precision. In the bullet cluster, The lensing mass peaks coincide closely with the galaxy concentrations associated with each of the two colliding clusters. This alignment indicates that whatever dominates the gravitational potential behaves dynamically like the galaxies, rather than like the gas. It moves through the collision largely unaffected by hydrodynamic forces and remains bound to the galaxy distribution. Quantifying the statistical significance of this alignment and offset requires careful analysis. Weak lensing mass reconstructions involve noise from intrinsic galaxy shapes, finite sampling, and smoothing. To assess whether the observed mass-gas separation could arise by chance, researchers performed extensive statistical tests, including bootstrap resampling and Monte Carlo simulations. These analyses consistently showed that the probability of the observed alignment occurring randomly is extremely small. The separation between mass and gas peaks exceeds the combined positional uncertainties by several standard deviations, often quoted at greater than 5 sigma significance. Projection effects were an obvious concern and were tested rigorously. Because gravitational lensing measures mass integrated along the line of sight, one might imagine that unrelated structures projected along the same line of sight could create apparent mass peaks offset from the gas. To address this possibility, researchers examined the redshift distribution of galaxies in the field and modeled alternative three-dimensional configurations. These tests showed that no plausible projection scenario could reproduce the observed alignment of mass peaks with galaxy distributions, while simultaneously explaining the displacement of the gas. Another projection-related concern is that the merger axis might be significantly inclined relative to the plane of the sky, causing apparent separations that do not reflect true physical offsets. However, as established by the sharpness and curvature of the X-ray shock front and by galaxy velocity measurements, the merger occurs predominantly in the plane of the sky. This geometry minimizes line-of-sight confusion and ensures that the observed offsets correspond closely to real spatial separations. The presence of two distinct mass peaks is a critical aspect of the discovery. If the system contained only a single mass concentration, interpretations would be more ambiguous. Instead, the lensing maps reveal two separate mass peaks, each associated with one of the colliding clusters. Both peaks are offset from the X-ray gas and aligned with their respective galaxy populations. This bilateral symmetry strongly constrains possible explanations. Any model invoking observational artifacts, projection effects, or unusual gas behavior would need to account for two independent offsets occurring in a consistent and physically motivated way. The two-peak structure also demonstrates that the offset is not caused by some peculiar property of a single cluster core. It is a systematic outcome of the collision affecting both components of the system. Each subcluster exhibits the same qualitative behavior: gas slowed and displaced, galaxies and dominant mass moving ahead. This repetition within a single system reinforces the interpretation that the effect arises from fundamental physical differences between components rather than from chance or special initial conditions. The temporal aspect of the separation is equally important. Numerical simulations of cluster mergers show that the mass-gas offset is short-lived on cosmological timescales. After core passage, gravitational forces begin to pull the gas back towards the potential wells defined by the dominant mass. Over a few 100 million years, the gas and mass distributions partially realign, reducing the observable separation. The bullet cluster is observed during the narrow window, when the offset is near its maximum. This short-lived nature explains both the rarity and the significance of the observation. Such systems are uncommon not because the underlying physics is exotic, but because the timing must be precise. Observing a cluster merger too early or too late would obscure the separation. The bullet cluster happens to be caught at exactly the right stage, making the offset large enough to measure cleanly. The transient nature of the offset also rules out explanations based on long-term equilibrium configurations. The separation is a dynamical effect produced by the collision, not a static arrangement that could be tuned or maintained indefinitely. This further strengthens the interpretation that the observed mass peaks correspond to a collisionless component that responds differently from the gas during the merger. Taken together, the spatial offset between gas and mass, the quantitative scale of the separation, the alignment with galaxy centroids, the high statistical significance, the rejection of projection effects, the presence of two distinct mass peaks, and the short-lived timing of the configuration form a coherent and internally consistent picture. The bullet cluster reveals, in a single snapshot, that most of the gravitating mass in a galaxy cluster is not where most of the luminous baryonic matter is. This realization sets the stage for interpreting the dominant mass component as something fundamentally different from gas or stars, governed by gravity but largely immune to the collisional processes that shape the visible plasma. Once the mass-light offset in the bullet cluster is established, a natural question follows. Could the mass traced by gravitational lensing simply be ordinary matter locked up in stars that are faint, diffuse, or otherwise hard to see? This possibility must be examined carefully because stars are collisionless like dark matter and move with the galaxies during a merger. However, multiple independent constraints show that stars cannot account for more than a small fraction of the total mass in galaxy clusters, and that increasing their contribution to explain the lensing signal would violate well-established observations. The most direct constraint comes from stellar mass-to-light ratios. The mass-to-light ratio relates how much mass is present in stars for a given amount of emitted light, typically measured in optical or near-infrared bands. These ratios are not free parameters. They are constrained by stellar evolution theory and by observations of stellar populations in galaxies. For old, metal-rich stellar populations typical of cluster ellipticals, mass-to-light ratios are higher than for young star-forming galaxies, but they remain within a relatively narrow range. Even under conservative assumptions that maximize stellar mass, the amount of mass implied by the observed light from cluster galaxies is far smaller than the mass required by lensing. The total luminosity of galaxies in a massive cluster can be measured by summing the light from individual galaxies over the cluster volume. In rich clusters, this total luminosity is large, but when converted into stellar mass using realistic mass-to-light ratios, it accounts for only a few % of the cluster's total gravitational mass. In systems like the bullet cluster, detailed photometric surveys show that the combined stellar mass of all galaxies falls well below 10% of the mass inferred from lensing, typically closer to 2 or 3%. This fractional contribution is remarkably consistent across massive clusters. Studies spanning a wide range of cluster masses and redshifts find that the stellar mass fraction rarely exceeds 5% of the total mass. This is not a coincidence, but a reflection of how inefficient star formation is in the deep potential wells of clusters. Most baryons in clusters remain in the hot intracluster medium rather than cooling and forming stars. This inefficiency places a hard upper limit on how much mass can plausibly be hidden in stars. One might argue that intracluster light could significantly increase the stellar mass budget. Intracluster light consists of stars that are not bound to any single galaxy, but instead orbit freely within the cluster potential, having been stripped from galaxies during interactions. This diffuse light is faint and difficult to detect, especially at large radii, raising the possibility that a substantial amount of stellar mass could be missed in standard surveys. However, deep imaging and careful measurements of intracluster light show that while it contributes meaningfully to the total stellar luminosity, it does not come close to bridging the mass gap. Even when intracluster light is included, the total stellar mass increases by at most a factor of 2 relative to the mass inferred from galaxies alone. This still leaves the stellar contribution well below the level required to explain the lensing mass. Moreover, intracluster light follows the overall cluster potential smoothly and does not form compact mass concentrations aligned with the lensing peaks seen in the bullet cluster. It therefore cannot account for the observed mass distribution even qualitatively. Stellar population synthesis models provide an additional layer of constraint. These models relate the integrated light of a stellar population to its mass by accounting for stellar lifetimes, initial mass functions, and chemical evolution. While uncertainties exist, especially regarding the low mass end of the initial mass function, extreme variations would be required to boost stellar mass-to-light ratios enough to explain the cluster mass. Such variations would have observable consequences, including altered galaxy colors, spectral features, and supernova rates, none of which are seen at the required level. Independent dynamical constraints reinforce this conclusion. The velocities of galaxies orbiting within a cluster provide a measure of the depth of the gravitational potential. If stars dominated the mass, then the potential inferred from galaxy velocities would closely track the distribution of stellar light. Instead, velocity dispersion measurements show that galaxies move in a much deeper potential than can be explained by the stellar mass alone. The inferred dynamical mass exceeds the stellar mass by more than an order of magnitude, a discrepancy that cannot be resolved by adjusting stellar parameters within reasonable bounds. Attempts to increase the stellar mass artificially to match the lensing signal lead to conflicts with other observations. Raising stellar mass-to-light ratios significantly would imply an overabundance of low-mass stars, which would alter galaxy spectra and colors in ways that are not observed. Increasing the total stellar mass would also increase the baryon fraction of clusters beyond the cosmic baryon fraction measured independently from the cosmic microwave background. This would imply that clusters somehow contain more baryons than the universe as a whole allows, an untenable conclusion. Furthermore, if stars dominated the mass, the spatial distribution of mass would closely follow the light. In the bullet cluster, the lensing mass peaks are offset from the brightest baryonic component, the gas, but they do not show the extreme concentration expected if stars were responsible for most of the mass. The mass distribution is smoother and more extended than the stellar light, consistent with a dominant dark component rather than with stars packed into galaxies. The collision dynamics themselves also argue against stellar dominance. Stars behave collisionlessly, but their total mass is too small to determine the gravitational potential. During the merger, the galaxies move ahead of the gas, but the gravitational potential traced by lensing moves with them because the dominant mass component does. If stars were responsible, their limited mass would be insufficient to anchor the potential wells observed. The lensing signal would instead be much weaker and more closely tied to the gas, which contains most of the baryonic mass. Taken together, these arguments leave little room for stars as the dominant mass component in galaxy clusters. Stellar mass-to-light ratios constrain how much mass can be hidden in luminous matter. The total luminosity of cluster galaxies sets a firm upper bound on stellar mass. Intracluster light increases this bound only modestly. Stellar population synthesis models prevent arbitrary increases in mass-to-light ratios. Galaxy velocity dispersions demand a much deeper potential than stars can provide. Attempts to inflate the stellar mass violate independent cosmological and observational constraints. The conclusion is not based on a single line of evidence, but on the convergence of many. Stars are an important component of clusters, but they are dynamically minor. They trace the gravitational potential. They do not create it. In the bullet cluster, this distinction is made explicit by the separation between the gas, the galaxies, and the total mass. The galaxies move with the dominant mass not because they carry it, but because both are governed by gravity and are effectively collisionless. The mass itself must therefore reside in something other than stars, something that contributes the bulk of the gravitational potential while remaining largely invisible to electromagnetic observation. The bullet cluster provides a rare opportunity to observe how different forms of matter respond to the same gravitational impulse under extreme conditions. Central to its interpretation is the conclusion that the dominant mass component behaves as collisionless on cluster scales. This term has a precise physical meaning in this context and is not a metaphor. It describes a regime in which particles interact so weakly with one another that, during a high-speed encounter, they pass through opposing structures without appreciable momentum exchange, drag, or energy dissipation beyond gravity. On cluster scales, collisionless does not imply an absolute absence of interactions. It means that the effective interaction cross-section per unit mass is small enough that the mean time between interactions vastly exceeds the duration of the merger. In practical terms, this means that during a collision lasting a few 100 million years, the dominant mass component experiences negligible non-gravitational scattering. Its motion is therefore governed almost entirely by gravity, just as with stars and galaxies, but unlike the hot plasma of the intracluster medium. This definition can be made quantitative. The key observable is the absence of measurable drag on the dominant mass component as the two clusters interpenetrate. If dark matter particles interacted significantly with one another, collisions between particles belonging to opposing halos would transfer momentum, producing a lag between the dark matter halo and the galaxy distribution similar to the lag observed in the gas. The fact that no such lag is detected places an upper limit on the dark matter self-interaction cross-section. In the bullet cluster, this upper limit is typically expressed as a cross-section per unit mass of order less than 1 square centimeter per gram. The exact numerical value depends on assumptions about the merger geometry, velocity, and halo density profiles, but the order of magnitude is robust. This limit is several orders of magnitude smaller than the effective interaction cross-section of the intracluster plasma, which is dominated by electromagnetic forces and collective plasma effects. For the gas, the effective interaction rate is high enough that momentum exchange and thermalization occur rapidly on merger timescales. For dark matter, the lack of such effects implies a fundamentally different interaction regime. Comparing dark matter to baryonic plasma highlights the contrast. In the intracluster medium, charged particles interact through long-range Coulomb forces, leading to efficient momentum transfer, even at low densities. Shocks form, kinetic energy is dissipated into heat, and bulk motion is rapidly altered. For dark matter, whatever its microscopic nature, no analogous mechanism operates at an appreciable rate. There is no evidence for shock formation, heating, or pressure support associated with the dark component. Instead, its distribution remains smooth and centered on the galaxy populations, indicating that it experiences the merger as a largely transparent event. This transparency explains why dark matter halos pass through each other during a cluster collision. As the two clusters interpenetrate, their dark matter halos overlap spatially for a brief period. If dark matter particles scattered frequently, this overlap would result in significant momentum exchange, heating of the halo, and potentially observable changes in halo shape or position. None of these effects are seen at the level required to explain the observations. The halos emerge from the collision largely intact, continuing along trajectories set by the pre-merger gravitational potentials. The lack of drag is a particularly strong constraint. Drag would manifest as a measurable offset between the dark matter halo and the galaxies, since galaxies are effectively collisionless test particles. In the bullet cluster, the lensing mass peaks are coincident with the galaxy centroids within observational uncertainties. This indicates that any drag force acting on the dark matter halo is too small to produce a detectable separation over the duration of the merger. From this absence, limits can be placed on the rate of momentum transfer between dark matter particles. These constraints are strengthened by the high relative velocity of the merger. Because the collision occurs at several thousand kilometers per second, any velocity-dependent interaction would be amplified. The fact that no drag is observed even under these extreme conditions implies that dark matter interactions must be weak across a broad range of velocities relevant to cluster environments. This is important because some particle models predict interactions that become stronger at low velocities. The bullet cluster tests the high-velocity regime directly. After the collision, dark matter halos do not remain permanently undisturbed. Gravitational interactions cause them to re-equilibrate over time. Tidal forces, phase mixing, and violent relaxation gradually reshape the halos, redistributing energy and angular momentum. This re-equilibration occurs on timescales comparable to the dynamical time of the cluster, typically of order 1 billion years. However, this process is purely gravitational and does not involve dissipation. It does not erase the collisionless nature of the dark matter. It simply reflects the system's evolution toward a new equilibrium configuration. The timescale of halo re-equilibration is long compared to the duration of the mass-gas separation observed in the bullet cluster. This is why the lensing mass peaks remain aligned with the galaxies, even as the gas begins to respond to the combined gravitational potential. The dark matter halos define the potential wells, and the gas gradually falls back toward them after being shocked and displaced. The halos themselves do not experience an analogous slowing or heating process. The implications for particle interaction models are significant. Any viable dark matter candidate must be consistent with the upper limits on self-interaction derived from cluster mergers. Models involving strongly interacting massive particles, composite dark matter with large cross-sections, or dark matter that couples appreciably to itself through new long-range forces are tightly constrained. At the same time, the bullet cluster does not rule out all forms of interaction. Weakly interacting particles, or particles with self-interactions below the derived limits, remain compatible with the data. It is also important to recognize what the bullet cluster does not constrain. It does not directly measure the mass of individual dark matter particles, nor does it determine whether they are fermions or bosons, cold or warm, annihilating or stable. The constraints apply specifically to elastic self-interactions at the velocities and densities characteristic of cluster environments. Other properties must be probed through complementary observations, such as cosmic microwave background measurements, large-scale structure, and laboratory experiments. Nevertheless, the bullet cluster provides one of the cleanest astrophysical demonstrations that the dominant mass component behaves in a way fundamentally different from baryonic matter. Its collisionless behavior is not inferred indirectly or through complex modeling, but observed directly through the absence of effects that should be present if interactions were strong. This absence is as informative as any positive detection. By showing that the dominant mass component passes through a violent collision without slowing, heating, or dispersing like gas, the bullet cluster isolates a key property of dark matter. It behaves as a collisionless fluid on cluster scales, interacting primarily through gravity. This property is not an assumption built into the interpretation. It is a conclusion forced by the data. Once established, it provides a powerful filter through which all proposed dark matter models must pass, anchoring theoretical speculation to an unambiguous observational reality. The bullet cluster presents an especially severe challenge for theories that attempt to explain cosmic mass discrepancies through modified gravity rather than through a dominant non-luminous mass component. While such theories have had empirical success in describing galaxy rotation curves, the physical regime and observational constraints of a violent cluster merger expose limitations that are difficult to overcome without reintroducing unseen mass in some form. A central element of many modified gravity approaches, particularly Mond-like formulations, is the introduction of a characteristic acceleration scale below which gravitational behavior departs from the Newtonian form. This scale is chosen to reproduce flat rotation curves in galaxies, where typical accelerations are extremely low. In massive galaxy clusters, and especially during mergers, the relevant accelerations are significantly higher. In the bullet cluster, the accelerations experienced by gas and galaxies during core passage lie well outside the regime where Mond effects are expected to dominate. This acceleration scale mismatch immediately undermines the applicability of Mond as a standalone explanation in this system. Even if one sets aside the acceleration scale issue, gravitational lensing introduces a deeper conceptual problem. Lensing responds to the gravitational potential integrated along the line of sight, not simply to local accelerations. Any modified gravity theory must therefore specify how space-time curvature is generated and how light propagates through it. In many formulations, reproducing the observed lensing strength requires additional degrees of freedom beyond the modified force law itself. These additions often behave effectively like an extra gravitating component, weakening the claim that no unseen mass is required. In the bullet cluster, lensing maps reveal mass concentrations that are spatially offset from the baryonic gas. Within a modified gravity framework alone, the gravitational potential should be closely tied to the distribution of visible matter, particularly the hot gas that contains most of the baryonic mass. The observed displacement between the lensing mass peaks and the gas therefore represents a fundamental inconsistency. Gravity, modified or not, acts on matter where it is. If the gas dominates the baryonic mass, the potential should follow it. The fact that it does not points to an additional source of gravity not associated with the gas. This leads to a critical requirement shared by many modified gravity models when applied to clusters: the introduction of an additional unseen mass component. This component is often hypothesized in the form of massive neutrinos or other weakly interacting particles. Once such a component is included, the conceptual distinction between modified gravity and dark matter-based explanations becomes blurred. The theory now depends on unseen matter to explain cluster-scale phenomena, eroding the original motivation for eliminating dark matter entirely. Reproducing the mass-gas separation observed in the bullet cluster is particularly difficult within a modified gravity-only framework. The separation arises because the gas experiences non-gravitational interactions that slow it down, while galaxies and the dominant mass component do not. Modified gravity does not naturally produce differential behavior based on collisional properties. Gravity acts universally on all forms of matter. Without a collisionless mass component that can move independently of the gas, there is no natural mechanism to generate the observed offset. Relativistic extensions of modified gravity attempt to address lensing and cosmology self-consistently by embedding modified dynamics within a covariant theory. While these theories can be constructed to match certain observations, they still struggle with systems like the bullet cluster. Achieving agreement with the lensing data while maintaining consistency with other constraints often requires finely tuned parameters or carefully chosen additional fields. This tuning diminishes predictive power and shifts the theory toward an empirical fitting exercise rather than a unified physical explanation. The contrast between empirical fitting and theoretical economy becomes stark in this context. Modified gravity theories are often valued for their apparent simplicity in describing galactic dynamics. In the bullet cluster, that simplicity evaporates. Multiple adjustments, supplementary components, and special assumptions are required to reproduce the observations. The resulting models may accommodate the data, but they do so at the cost of explanatory coherence. The bullet cluster is therefore a worst-case scenario for modified gravity. It combines high accelerations, strong gravitational lensing, violent non-equilibrium dynamics, and a clear spatial separation between baryonic matter and the dominant gravitational potential. Each of these elements stresses the assumptions of modified gravity. Together, they leave little room for maneuver without reintroducing unseen mass. Crucially, the difficulty lies not in matching a single number or trend, but in reproducing the geometry of the system. The gravitational potential inferred from lensing is in the wrong place relative to the visible matter. This is a spatial, structural failure rather than a parametric one. It cannot be fixed by rescaling a force law or adjusting an acceleration threshold. It requires additional gravitating material located where the lensing peaks are observed. In contrast, a framework that includes a dominant collisionless mass component accounts for the bullet cluster with minimal additional assumptions. Gas slows through well-understood plasma physics. Galaxies and the dominant mass component pass through the collision largely unaffected. The gravitational potential follows the collisionless component, producing the observed lensing map. Each step follows directly from established physical principles applied to different forms of matter. For this reason, the bullet cluster remains a cornerstone empirical argument against modified gravity as a complete explanation of cosmic mass discrepancies on cluster scales. It does not rely on subtle statistical inferences or fine-tuned modelling. It presents a direct, spatially resolved comparison between where visible matter is and where gravity acts, and in doing so, it exposes the fundamental difficulty of explaining the system without invoking a dominant, non-luminous mass component. Claims about mass-light separation in a system as complex as the bullet cluster carry weight only insofar as they withstand aggressive statistical scrutiny. The conclusion that the dominant mass distribution is offset from the baryonic gas is not based on a single reconstruction, a single algorithm, or a visually compelling overlay. It rests on a layered error analysis designed to test whether the result could plausibly arise from noise, bias, or methodological choice. Across these tests, the separation persists with high statistical significance, placing it well outside the regime of marginal detection. A primary source of uncertainty in weak gravitational lensing arises from shape noise. Background galaxies are not intrinsically round. They possess a wide distribution of ellipticities due to their own morphology and orientation. The lensing-induced shear is typically only a few % effect, far smaller than the intrinsic shape variations. As a result, individual galaxy shapes carry little information. The lensing signal emerges only statistically by averaging over large numbers of galaxies. The variance associated with this intrinsic ellipticity distribution defines the dominant noise term in weak lensing analyses. In the bullet cluster, the surface density of usable background galaxies is unusually high due to deep imaging and favorable redshift geometry. This reduces shape noise by increasing the number of independent samples contributing to each region of the shear field. Even so, shape noise remains a fundamental limitation, and its impact is explicitly propagated through all mass reconstructions. Importantly, shape noise produces random fluctuations in the inferred mass distribution. It does not generate coherent, spatially aligned mass peaks unless reinforced by real gravitational signal. To quantify the effect of shape noise and sampling variance, bootstrap resampling is employed. In this approach, the background galaxy catalogue is repeatedly resampled with replacement, and the full lensing reconstruction is repeated for each resampled dataset. The resulting ensemble of mass maps provides a direct measure of the variability induced by finite sampling. In the bullet cluster, bootstrap realizations show that while the detailed morphology of low-level features can vary, the locations of the dominant mass peaks are remarkably stable. The centroids of these peaks cluster tightly around the same positions across realizations. Monte Carlo reconstructions extend this approach by simulating mock lensing datasets with known input mass distributions, noise consistent with the observed shape distribution, measurement uncertainties, and background galaxy density is added, and the reconstruction pipeline is applied blindly. These simulations test whether the analysis method itself introduces biases or spurious structures. When applied to bullet cluster-like configurations, the reconstructions recover the input mass peaks with high fidelity and do not produce systematic offsets between mass and gas unless such offsets are present in the input model. Sensitivity to background galaxy selection is another critical concern. Contamination of the background sample by unlensed foreground or cluster galaxies would dilute the shear signal and could bias mass estimates. To address this, strict color magnitude cuts are applied to remove galaxies consistent with the cluster redshift. Photometric redshifts, when available, provide an additional layer of filtering. Analyses are repeated with different selection criteria to test robustness. While the overall normalization of the mass map can vary slightly depending on selection, the positions of the mass peaks remain unchanged within uncertainties. Systematic uncertainties in the location of mass centroids are carefully quantified. These uncertainties arise from several sources: finite resolution due to smoothing, residual shape noise, and reconstruction algorithm choices. The effective resolution of a lensing mass map is set by the smoothing scale required to suppress noise, typically tens of kiloparsecs. In the bullet cluster, the observed separation between the mass peaks and the gas peak is substantially larger than this resolution scale. Centroid uncertainties are therefore much smaller than the measured offsets. Different reconstruction methods, such as direct inversion techniques, maximum likelihood approaches, and parametric modeling, have been applied independently to the same data. While these methods differ in their assumptions and implementation details, they consistently locate the dominant mass peaks in the same regions. This convergence across methods reduces the likelihood that the result is an artifact of any particular algorithm. Cross-validation by independent teams provides one of the strongest tests of robustness. Multiple groups using different telescopes, different shape measurement pipelines, and different reconstruction codes have analyzed the bullet cluster lensing data. These analyses were often conducted years apart and with improved data quality over time. Despite these differences, the central result, the alignment of mass peaks with galaxies and their offset from the gas, has been reproduced repeatedly. Independent confirmation is a powerful safeguard against unconscious bias or methodological blind spots. The statistical significance of the mass-gas separation can be quantified by comparing the measured offset to the combined uncertainties in the centroid positions. When this is done, the separation exceeds 5 standard deviations in many analyses. A significance at this level corresponds to a probability of chance alignment far below 1 in a million. Such a result is not sensitive to modest changes in assumptions or data selection. It requires a coherent signal present across the dataset. It is also important to note that the separation is observed for 2 distinct subclusters within the same system. Each subcluster exhibits its own mass peak, aligned with its galaxy population and offset from the gas. The probability that noise or systematics would independently produce 2 consistent offsets with the same qualitative behavior is vanishingly small. This internal replication within a single system further strengthens the statistical case. A marginal detection is one that disappears under reasonable changes in methodology, data quality, or assumptions. The bullet cluster result does not behave this way. Removing subsets of background galaxies, altering smoothing scales within acceptable ranges, or changing reconstruction techniques does not eliminate the separation. At most, such changes slightly alter the precise centroid locations or the sharpness of features, not the fundamental geometry of the mass distribution. Systematic effects that could, in principle, mimic a separation, such as anisotropic point spread function correction errors or large-scale image distortions, have been investigated and ruled out. These effects tend to produce correlated distortions across the field, not localized mass peaks aligned with galaxy distributions. Moreover, their signatures would appear in control fields and in other cluster observations processed with the same pipelines, which is not observed. The robustness of the result is further reinforced by consistency with independent lines of evidence. Galaxy velocity dispersions indicate deep potential wells at the locations of the lensing peaks. X-ray observations show that the gas is displaced in exactly the direction expected from ram pressure during the collision. The lensing mass peaks occupy the dynamically expected positions for collisionless components. These independent observations all point to the same physical interpretation. In statistical terms, the bullet cluster mass light offset is an overdetermined result. It is supported by multiple data sets, multiple methods, multiple teams, and multiple physical diagnostics. Each layer of analysis constrains the others, leaving little room for an alternative explanation rooted in statistical fluctuation or systematic error. For these reasons, the bullet cluster is not cited as suggestive or intriguing evidence. It is cited as decisive. The separation between mass and baryonic light is not a borderline signal extracted from noisy data. It is a high-significance, spatially resolved feature that persists under exhaustive testing. The statistical robustness of this result is what elevates the bullet cluster from an interesting merger to one of the most compelling empirical demonstrations of a dominant, collisionless mass component in the universe. The scientific impact of the bullet cluster does not rest solely on its singularity. Its importance is amplified by the fact that it is no longer alone. In the years following its detailed study, astronomers actively searched for other merging galaxy clusters in which baryonic gas and gravitational mass might separate under collision. These efforts were motivated by a straightforward question: was the bullet cluster an anomaly or a representative example of a broader physical phenomenon? The answer, built gradually through observation and replication, strongly favours the latter. Several other dissociative cluster mergers have since been identified and studied using the same combination of X-ray observations and gravitational lensing. Systems such as MAX J0025.4-1222, Able 2744 and El Gordo demonstrate similar qualitative behaviour: hot intracluster gas displaced from the dominant mass peaks, with those mass peaks aligned with galaxy concentrations rather than with X-ray brightness. While none of these systems match the bullet cluster in every respect, the recurring pattern is unmistakable. Across this growing sample, mass-gas offsets are consistently observed whenever the merger geometry and timing allow them to be resolved. The offsets vary in magnitude, orientation and clarity, reflecting differences in collision velocity, impact parameter, mass ratio and viewing angle. In some systems, the separation is dramatic and easily visible. In others, it is subtler and requires deeper data or more careful analysis. Importantly, no well-studied dissociative merger has shown the opposite behaviour, a dominant lensing mass peak tracking the gas while ignoring the galaxies. Differences in merger velocity play a central role in shaping these systems. High-velocity mergers, like the bullet cluster, produce strong shocks, large ram pressure forces, and rapid gas displacement. Lower velocity mergers still separate gas from collisionless components, but the separation may be smaller and shorter-lived. Geometry is equally important. Mergers occurring close to the plane of the sky maximize observable offsets, while mergers oriented closer to the line of sight compress spatial separations into projection and reduce their apparent significance. These variations explain why the bullet cluster remains the cleanest and most pedagogically powerful case. It combines an unusually high relative velocity, a favourable plane of sky orientation, a clear post-core passage timing, and exceptionally high-quality X-ray and lensing data. Other systems may match one or two of these criteria, but rarely all of them simultaneously. The bullet cluster is therefore not typical in appearance, but it is typical in physics. As observational samples have grown, so has statistical confidence. Early studies relied on individual showcase systems. Modern analyses now examine ensembles of merging clusters selected through X-ray surveys, Sunyaev-Zeldovich surveys, and optical cluster catalogues. In these samples, dissociative mergers consistently show mass-gas offsets when observed at the appropriate stage. This consistency across independent systems and selection methods reinforces the interpretation that the effect is physical rather than coincidental. The diversity among follow-up systems also provides additional information. Variations in offset magnitude and halo morphology constrain how strongly dark matter can interact with itself. If dark matter had even modest self-interaction cross-sections, some mergers would show partial drag effects, halo deformation, or delayed halo centroids relative to galaxies. Instead, the dominant mass components consistently behave as collisionless across a range of velocities and environments. This allows upper limits on interaction strength to be refined and cross-checked across multiple systems rather than inferred from a single example. Large cluster surveys play a crucial role in this process. Wide-area X-ray surveys identify dynamically disturbed clusters. Optical surveys provide galaxy distributions and photometric redshifts. Weak lensing programs map mass distributions over wide fields. Together, these surveys create a pipeline for discovering and characterizing new merging systems. As data quality improves, particularly with deeper imaging and higher resolution X-ray observations, the number of usable dissociative mergers continues to increase. Replication is especially important because it removes dependence on exceptional circumstances. The bullet cluster is compelling precisely because it is extreme, but replication shows that the underlying behavior does not require extremity. The same physical separation between collisional gas and collisionless mass appears wherever the conditions permit it to be seen. This transforms the bullet cluster from a singular argument into the most vivid example of a general rule. What emerges from this growing body of evidence is not a collection of curiosities, but a consistent physical narrative. Cluster mergers act as large-scale particle experiments. Gas behaves as a collisional plasma. Galaxies behave as nearly collisionless tracers. The dominant gravitating mass behaves like the galaxies, not like the gas. The bullet cluster simply made this separation impossible to ignore. For this reason, later discoveries did not weaken the bullet cluster's importance. They strengthened it. Each additional system reduces the probability that the original observation was a fluke, a projection artifact, or a methodological error. Together, they establish that the bullet cluster is not an outlier in physics, only in clarity. It remains the cleanest case not because others contradict it, but because they confirm it under less favourable conditions, reinforcing the same conclusion again and again through independent replication. The bullet cluster is often invoked in discussions of dark matter particle physics, but its role is frequently misunderstood. It does not function as a particle detector in the traditional sense, nor does it probe microscopic properties in isolation. Instead, it constrains dark matter through its macroscopic behavior under extreme astrophysical conditions. These constraints are powerful precisely because they are direct, geometric, and largely independent of detailed modelling assumptions. What the bullet cluster constrains most directly is the self-interaction strength of dark matter on cluster scales. The observed behaviour of the dominant mass component during the collision shows that it passes through the opposing cluster with little to no measurable drag. From this, an upper limit can be placed on the self-interaction cross-section per unit mass. If dark matter particles scattered off one another at an appreciable rate, momentum exchange would slow the dark matter halos relative to the galaxies, producing a detectable offset similar to that seen in the gas. The absence of such an offset constrains the interaction rate. These limits are typically expressed as an upper bound of order less than 1 square centimetre per gram, with conservative analyses often tightening this bound further, depending on assumptions about merger velocity, geometry, and halo density profiles. While the precise numerical value varies slightly between studies, the qualitative conclusion is robust. Dark matter self-interactions must be weak enough that, even in a high-speed cluster collision, the cumulative effect is negligible. Equally important is what the bullet cluster does not constrain. It does not determine the mass of individual dark matter particles. Whether the particles are extremely light or extremely heavy is largely irrelevant to the collision dynamics, as long as they behave collectively as a collisionless fluid. The system also does not constrain annihilation rates, decay channels, or coupling strengths to standard model particles. These properties influence indirect detection signals or early universe behavior, not the large-scale gravitational response seen in cluster mergers. This distinction highlights why the bullet cluster complements, rather than competes with, laboratory searches. Direct detection experiments and collider searches attempt to measure rare interactions between dark matter and ordinary matter or to produce dark matter particles directly. Their sensitivity depends on specific assumptions about particle mass and interaction channels. The bullet cluster, by contrast, constrains dark matter through its absence of interaction with itself under astrophysical conditions. It rules out broad classes of models, regardless of how elusive the particles may be in the laboratory. The comparison between self-interaction limits from clusters and laboratory limits is therefore asymmetric. Laboratory experiments probe dark matter-baryon interactions at small scales and low energies. The bullet cluster probes dark matter interactions at high velocities and over enormous path lengths. A particle could evade all current laboratory detection while still being excluded by cluster-scale self-interaction limits, and vice versa. Together, these approaches carve out the allowed parameter space from different directions. A key conceptual distinction clarified by the bullet cluster is the difference between weakly interacting and collisionless behavior. Weak interaction, in a particle physics sense, refers to coupling through the weak nuclear force. Collisionless behavior, in an astrophysical sense, refers to the effective absence of momentum exchange on macroscopic timescales. Dark matter could, in principle, interact through forces unrelated to the weak interaction and still behave collisionlessly in clusters if those interactions are sufficiently rare. The bullet cluster constrains collisionlessness, not the specific particle physics origin of that property. The observations strongly favour models in which dark matter is cold, meaning non-relativistic at the time of structure formation. Cold dark matter naturally forms extended halos with well-defined gravitational potentials that pass through one another during mergers without dissipating energy. Warm or hot dark matter models, while not ruled out solely by the bullet cluster, struggle to reproduce the observed halo structure and merger dynamics when combined with other cosmological constraints. The bullet cluster fits cleanly within the cold dark matter framework without requiring special adjustments. Strongly interacting dark matter models are particularly disfavored. Any model in which dark matter particles experience frequent collisions would predict observable consequences during a cluster merger, halo deformation, heating, or lag behind the galaxies. None of these effects are seen at the level required. This exclusion is broad and does not depend on fine details. It rules out entire classes of models in which dark matter behaves more like a collisional fluid than like a collisionless component. The bullet cluster's constraints gain additional power when combined with observations of the cosmic microwave background. The microwave background encodes the matter content of the universe at early times and constrains the total dark matter density and its role in structure formation. These constraints are sensitive to dark matter's gravitational influence and its interactions in the early universe. When combined with the bullet cluster's constraints on late-time, high-velocity self-interactions, a consistent picture emerges. Dark matter must behave as a cold, effectively collisionless component across a vast range of epochs and environments. This complementarity is crucial. A model that fits the cosmic microwave background but predicts significant self-interactions at cluster velocities is ruled out by the bullet cluster. Conversely, a model that behaves collisionlessly in clusters but disrupts early universe structure formation is ruled out by the microwave background. Only models that satisfy both survive. The bullet cluster, therefore, does not answer the question of what dark matter is at the particle level. It answers a different, equally fundamental question: how dark matter behaves when subjected to extreme gravitational stress. The answer is clear. It behaves as a collisionless component, interacting negligibly with itself beyond gravity, even during one of the most violent events the universe can produce. This behavioral constraint is among the most direct and least model-dependent pieces of evidence in dark matter physics. It does not rely on subtle statistical correlations or on assumptions about unseen processes. It relies on geometry, motion, and the absence of effects that would otherwise be unavoidable. In doing so, the bullet cluster sharply narrows the landscape of viable dark matter theories and anchors particle speculation to an inescapable astrophysical reality. The bullet cluster does not exist in isolation from cosmology. Its significance extends well beyond the physics of a single merger and reaches directly into how structure forms and evolves in the universe. When interpreted within the broader cosmological framework, the system functions as a stringent, non-linear test of the standard picture of structure formation, one that probes regimes inaccessible to linear theory or early universe observations alone. At the core of this framework is the lambda CDM model, which describes a universe dominated by cold dark matter and dark energy, with ordinary baryonic matter playing a dynamically secondary role. In this model, dark matter collapses first into gravitationally bound halos, forming the scaffolding on which baryons later accumulate. Galaxy clusters represent the largest bound structures formed through this hierarchical process, assembling via successive mergers of smaller halos over cosmic time. The bullet cluster fits naturally into this picture as a late-stage merger between two massive halos that formed independently before colliding. Cosmological simulations based on lambda CDM predict that cluster-scale halos should be common by intermediate redshifts, and that mergers between them, while rare at extreme velocities, are inevitable over the age of the universe. The bullet cluster's mass scale, halo structure, and overall dynamical state are consistent with these expectations. While its relative velocity is high, it lies within the tail of the distribution produced by large volume simulations rather than outside it. This matters because it places the system within the predicted statistical landscape rather than requiring new physics to explain its existence. Merger rates in simulations provide an important context for interpretation. In lambda CDM, the growth of structure is driven by gravity acting on initially small density perturbations. As halos grow, mergers become less frequent but more energetic. Simulations show that major mergers between massive clusters are uncommon but not forbidden, especially at moderate redshifts where large-scale structure is still actively evolving. The bullet cluster occupies this regime. Its rarity is therefore a reflection of hierarchical growth statistics, not a contradiction of the model. Dark matter's role in large-scale structure formation is central to understanding why systems like the bullet cluster can exist at all. Dark matter provides the gravitational wells that allow matter to collapse efficiently. Without it, baryonic matter would struggle to overcome pressure forces, radiation coupling, and thermal motion, especially in the early universe. In a universe composed only of baryons, structure formation would be delayed and suppressed, and forming objects as massive as galaxy clusters by the observed epochs would be extremely difficult. This limitation becomes explicit when considering cluster formation. Baryons interact electromagnetically and therefore heat up, radiate and resist compression. Without the deep, non-dissipative gravitational potential provided by dark matter, baryons alone cannot collapse into cluster-scale structures on the observed timescales. Even if clusters could eventually form, their internal dynamics and mass distributions would differ markedly from what is observed. The bullet cluster's mass, temperature, and velocity structure all point to a dominant non-baryonic component shaping the gravitational potential. The bullet cluster is especially valuable because it probes the non-linear regime of structure formation. Many cosmological tests rely on linear or quasi-linear perturbations, such as fluctuations in the cosmic microwave background or galaxy clustering on large scales. Cluster mergers, by contrast, involve highly non-linear dynamics, strong shocks, violent relaxation, and rapid changes in gravitational potential. Success in this regime is a demanding test of any cosmological model. N-body simulations that include only collisionless dark matter have long predicted that halos should pass through one another during mergers, largely preserving their identity identity while their baryonic components behave differently. When hydrodynamics is added to these simulations, the gas is stripped, shocked, and displaced, while the dark matter halos remain aligned with the galaxies. The bullet cluster closely matches these predictions. The observed separation between gas and mass, the survival of distinct halos, and the subsequent re-equilibration of the system all follow directly from simulated merger dynamics in a lambda CDM universe. Agreement between observation and simulation is not limited to qualitative features. Quantitative aspects such as the scale of the separation, the persistence of halo structure, and the time scale over which gas falls back toward the gravitational potential are consistent with numerical results. This agreement is non-trivial. It indicates that the same set of physical assumptions can explain both the large-scale statistical properties of the universe and the detailed dynamics of an extreme individual system. The bullet cluster also strengthens the standard model by constraining alternatives. Any cosmological framework that seeks to replace dark matter must not only reproduce galaxy rotation curves or background radiation statistics, but also explain how massive clusters form, merge, and behave under extreme conditions. The bullet cluster demonstrates that gravity alone, acting on baryons, is insufficient to account for observed cluster dynamics. It shows that a dominant collisionless component is required not just in the linear growth of structure, but in its most violent, nonlinear expressions. In this sense, the bullet cluster functions as a bridge between cosmology and astrophysics. It connects early universe initial conditions to late-time structure through a concrete, observable process. The same dark matter that shapes the acoustic peaks of the cosmic microwave background and the distribution of galaxies on large scales is responsible for the gravitational behavior seen in this merger. The consistency across these vastly different scales reinforces the coherence of the standard cosmological model. Rather than standing as an isolated anomaly, the bullet cluster strengthens confidence in lambda CDM by showing that its predictions hold under extreme conditions. It confirms that dark matter halos form, merge, and interact exactly as required to build the observed universe. In doing so, it demonstrates that the standard model is not merely a successful fit to averaged data, but a physically robust framework, capable of explaining both the calm, large-scale structure of the cosmos and the most violent events within it. The bullet cluster continues to be cited not because it is old, dramatic, or visually striking, but because it satisfies a rare set of scientific conditions that few systems meet simultaneously. It offers a clean, spatially resolved separation between different mass components under extreme dynamical stress, and it does so in a way that minimizes dependence on uncertain modeling assumptions. This combination has proven difficult to surpass, even as observational data have improved and new systems have been discovered. The most important reason for its enduring relevance is the clean separation of mass components. In the bullet cluster, the hot intracluster gas, the galaxies, and the dominant gravitating mass are physically displaced from one another in a way that directly reflects their interaction properties. Gas slows and lags due to hydrodynamic forces. Galaxies pass through largely unaffected. The dominant mass component follows the galaxies rather than the gas. This separation is spatial, measurable, and internally consistent across independent datasets. It does not rely on subtle statistical trends or inferred correlations. It is visible in the geometry of the system itself. This clarity translates into minimal model dependence. The key conclusions drawn from the bullet cluster do not hinge on assuming hydrostatic equilibrium, spherical symmetry, or detailed baryonic feedback prescriptions. X-ray observations identify where the gas is. Optical observations identify where the galaxies are. Gravitational lensing identifies where the mass is. The interpretation follows directly from comparing these maps. Even if one changes cosmological parameters, modifies gas physics details, or alters reconstruction techniques within reasonable bounds, the fundamental separation remains. Observational clarity matters more than aesthetic appeal. Many clusters are visually impressive, but their complexity obscures physical interpretation. Turbulence, projection effects, and overlapping substructures can make it difficult to disentangle cause and effect. The bullet cluster is unusually legible. Its merger geometry is favourable, its shock front is well defined, and its mass peaks are separated by distances well above observational resolution limits. This legibility is why it is used as an example in scientific papers, lectures, and textbooks. It shows the physics without requiring extensive caveats. The system has also assumed an educational role in astrophysics. It serves as a concrete demonstration of how different observational techniques probe different physical components of the universe. Students and researchers can see in one system why X-ray brightness does not trace mass, why galaxy light is an incomplete guide to gravity, and why gravitational lensing is uniquely powerful. Few examples communicate these lessons as directly or as convincingly. One might ask why newer data and newly discovered systems have not replaced the bullet cluster as the canonical example. The answer is not that newer systems contradict it, but that they tend to be messier. Many follow-up mergers confirm the same underlying behavior, but lack one or more of the bullet cluster's advantages: extreme velocity, clear timing, near-core passage, or a plane of sky orientation. As a result, they reinforce the interpretation without surpassing the original in clarity. The bullet cluster remains the cleanest realization of the phenomenon, not the only one. Importantly, the bullet cluster's interpretation is falsifiable. If future observations were to reveal a similar system in which the dominant lensing mass followed the gas rather than the galaxies, or in which dark matter halos exhibited clear drag relative to galaxies, the standard interpretation would be seriously challenged. Likewise, a convincing demonstration that projection effects or systematic errors could generically produce the observed offsets would undermine the conclusion. The fact that none of these falsifiers have materialized, despite years of scrutiny and improved data, strengthens confidence rather than eroding it. The system also remains a benchmark because it isolates a fundamental physical distinction: collisional versus collisionless behavior. This distinction is not specific to any particular dark matter model or cosmological parameter choice. It is a property of how matter responds to interaction. The bullet cluster shows that the dominant mass component behaves collisionlessly under conditions where baryonic matter demonstrably does not. That statement is independent of debates about particle mass, annihilation channels, or detection strategies. Finally, the bullet cluster endures because it connects scales. The same dark matter invoked to explain cosmic microwave background anisotropies and large-scale structure formation is seen here responding correctly in a violent, non-linear event. This continuity across regimes is rare. Many cosmological tests operate in averaged or linear domains. The bullet cluster shows that the same framework works when pushed to extremes. For these reasons, the bullet cluster remains a benchmark system. It is not cited out of habit or nostalgia, but because it continues to satisfy the highest standards of empirical clarity, robustness, and explanatory power. New data have not replaced it, they have contextualized it, and in doing so, they have confirmed what the bullet cluster first made unmistakable: that gravity in the universe is dominated by a component that is invisible, collisionless, and essential for making sense of how cosmic structures behave.